Hello, welcome to Fundamentals of Acoustics. This is the third week of this present course. In the last week, we had concluded the last week by discussing Bode plots, and specifically we had covered the phase and the magnitude plots for a simple 0 and a simple pole. What we will do this week is we will continue that discussion on Bode plots by developing magnitude plots for more complex functions for illustration purposes, and once we are done with that, we will proceed to developing one dimensional wave equation for sound propagation. So, in this particular module, which is today, we will continue our discussion on Bode plots. So, as I mentioned, what we are going to discuss today is Bode plots, and specifically we will do it for magnitude, for complex transfer functions. So, we will do it by an example. So, let us say that there is some system which has a transfer function defined as s square minus 4 divided by s square plus 4s plus 5. So, the first step when I have a complex transfer function which is not just a simple pole or a simple 0 is that I factorize the numerator. So, the numerator can be factored as s minus 2 and s plus 2, and the denominator can be factorized in terms of its linear factors as s plus 4. I am going to change this. So, this will be s square plus 5s plus 4. So, I can factorize it as s plus 4 and s plus 1. So, this I can write it as a transfer function h1 times a transfer function h2 divided by two other transfer functions h3 and h4, where h1 equals s minus 2, h2 equals s plus 2, h3 equals 1 over s plus 4 and h4 equals 1 over s plus 1. So, the way we develop a Bode magnitude plot for this type of a transfer function is that first we develop Bode magnitude plots for individual linear factors, and then we add them up. So, this is h3 is s plus 4 and this is s plus 1. Okay. Or actually a better way would be, because that will make mathematics slightly easier, is I multiply by h3 times h4. So, h3 and h4 are defined like inverse of s plus 4 and s plus 1. So, as I mentioned earlier, we develop magnitude plots for each of these individual transfer functions and then we add them up. So, the overall transfer functions, if I calculate it in decibels, is equal to 20 log of 10 h1, h2, h3, h4. So, it is equal to 20 log of 10 h1 plus 20 log of h2 plus 20 log of h3 plus 20 log of H4. So, if there are multiples or several factors, several individual transfer functions, and I have multiplied them up, then the overall transfer functions Bode plot as seen in this relation, because we are doing it on a log scale, is just the sum of individual Bode plots. So, our aim will be to develop Bode plots for each of these individual factors, and once we are able to do that, then we just add them up and develop the final plot. So, we will do these one by one. So, Bode plot for H1 it is dB equals 20 log of H1, and when we are doing Bode plots, S is equal to j omega. So, dB equals 20, and we also know that H1 equals S minus 2. So, what I get is j omega minus 2. Okay. Now, this is a simple 0 type of a function. So, I know as we saw it in the earlier class, that the Bode plot for magnitude for this function has two lines. The first line is the low frequency asymptote, and the second line is the high frequency asymptote. The low frequency asymptote corresponds to the condition when omega goes to 0. So, low frequency asymptote, so on the x axis I am going to plot log of omega, and on the y axis it is going to be in decibels, and this is what we are doing for H1. So, the low frequency asymptote is a straight line, and this value when omega approaches 0, the straight horizontal line, its value is going to be 20 log of minus 2 parenthesis. Okay. So, it is not negative of 20 log 2, but it is, so essentially it is 20 log 2 times 20 times log of 2, and the high frequency asymptote is 20 log of j omega. So, it is going to be a line with a positive slope, and this slope is 20 dB per decade, and the point of intersection of this curve is going to be where log of omega is going to be same as log of 2. So, this is this thing, log of minus 2, log of absolute value of negative 2. So, this is my Bode plot for H1, and the red curve is the actual curve, actual decibels, where the dark blue line is for the asymptotic response. Okay. So, the next thing we do is Bode plot for H2. So, this is equal to dB equals 20 log of absolute value of H2, and once I do the substitution S equals j omega and H2 is S plus 2, what I get is 20 log of j omega plus 2. Now, I can draw the Bode plot for this, but I need not do this in this particular case, because I see that or actually I will just do that for sake of completeness. So, the Bode plot for this will once again so that is the Bode plot for H2, the magnitude plot for H2. Now, when you compare the magnitude plot for H1 and H2, shape wise they are identical because both of them correspond to a simple 0, but also in terms of values they are identical because this value log of absolute value of 2 and log of absolute value of negative 2 is same, and also the crossover point in H1 is log of absolute value of negative 2 and log of absolute value of 2. So, these Bode plots for H1 and H2 they just turn out to be same, and the reason is that this term and this term, these two terms, they have the same absolute magnitude. So, what this means is that if the absolute magnitude of the 0 is same, then the Bode plot for simple zeros will be same. The value of 0 could be positive or negative or even complex, but as long as its absolute magnitude is same, then the magnitude plot is going to be the same. The phase plot may still not be the same because when we calculate the phase, it will depend on what is the real component and what is the imaginary component. But as long as the value of the 0, absolute value of the 0 is same, the Bode plot for a simple 0 is going to be the same thing. So, this is for H1 and H2, and next we will develop Bode plots for H3 and H4. So, we are going to directly develop the Bode plots because I think we have done sufficient amount of practice. So, so H3 and H4 are simple poles. They are simple poles. Okay. So, what that means is that their Bode plots. So, my horizontal axis in both these cases is log of omega, and on the vertical axis or y axis I have decibels. So, the Bode plots for these two guys, because they are both of them are simple poles, is going to be the low frequency asymptote is going to be a horizontal line, and then the high frequency asymptote is negatively sloped line. Same thing here. Okay. And the value here is going to be 20 log 1 by 4 for H3, and in this case it is going to be 20 log 1 by 4 for, oh I am sorry, this is going to be, it is going to be 1 over 1. Okay. So, this is going to be for H3 and this is going to be for H4, and the crossover points are going to be, so crossover point is going to occur when log of 1 over omega is going to be log of 1 over 4. So, which means this is going to be log of 4 and this is going to be log of 1. So, what we have done is we have constructed all the 4 Bode plots for individual factors, linear factors for H1, H2, H3 and H4, and we have seen that the curve for H2 is same as curve for H1. So, I am going to also write it same as here. Also, in H3 and H4 the actual response for simple poles is going to be like this, it is going to be below the asymptotic response. In zeros, simple zeros it is above, in simple zero poles it is below the asymptotic response. So, now I make some observations. So, what is my next step? My aim is to develop the Bode plot for the entire function. So, what I do is I add up the Bode plots. And the way I add up it is that on the frequency range I see what are the breakpoints where the curve is expected to change. Okay. So, I construct a table. So, the first range is 0 to 1 because the Bode plot for H4 changes its slope after 1. The next breakpoint is 2 because H2 and H1 they change at 2. So, basically I one to 2, that is the next range for omega. Then we see that H3 changes its slope at 4. So, my next range is going to be 2 to 4. In this range, in these individual ranges the shape of the curve is not going to change, and then the next and final range is 4 to infinity. So, I will fill up this table. So, what we are going to do is we are going to list down contributions of individual transfer functions H1, H2, H3, H4, and then we are going to total it up. So, the contribution from H1 in the range 0 to 1 is, so we look at it, contribution from H1 in the range 0 to 1. So, this is 20 log 2, 20 log 2. Contribution from H2 is also 20 log 2. Contribution from H3 is in this range 20 log 1 by 4, right, and contribution from H4 is 20 log 1 over 1, which is 0, log of 10, log of 1 is 0. So, when I add these up, the total decibels log 2 plus log 2 is 2 log 2, and log of 1 over 4 is log of 1 over 4 is minus of log 4. So, the H1, H2 and H3 will add up to cancel each other, and H4 is anyway 0. So, in the range 0 to 1, the contribution from overall contribution is going to be 0 decibels. Okay. And we can fill up all other parts of the table, but it just turns out that at least in this case we do not necessarily have to fill up all the other parts of the table. So, what we will do is we will now construct the overall Bode plot. So, overall Bode plot vertical axis in decibels. So, first we will do is we will mark down different points. So, first is 0 to 1. So, this is log of 1, then 1 to 2. So, this is log of 2, then 1 to 4, 2 to 4. So, this is log of 4, and then 4 to infinity. So, in the range 0 to 1, the contribution is 0 decibels. From 1 to 2, what we see is that contribution from H1 is still the same, it does not change. From H2 it is still the same, because H1 and H2 are same up to 2, and for H3 it is still the same, but from H4 I have a negatively sloped line. When we look at H4, after 1 the high frequency asymptote takes over. So, what that means is that the contribution from H1, H2, 3, H3 still remains 0, but because of H4 the overall curve starts sloping down. Okay. So, actually I am going to modify this curve a little bit so that I can draw easily. So, I am going to draw, so this is 0 decibels. So, after this it is going to be minus 20 decibels per decade. This is going to be the slope. Okay. Now, let us see what happens to the range 2 to 4. In the range 2 to 4, when we look at H2 and H1, after 2 the slope is positive, and it is 20 decibels per decade. So, the overall slope of this H1 and H2 will become 40 decibels per decade. So, this is 20 decibels per decade, 20 decibels per decade. This is still 0, 20 log 1 over 4, I am sorry, 20 log 1 over 4, okay, and this is negative. So, what that means is that the contribution from H1 and H2 will make sure that this, so I am getting 20 decibels, positive 20 decibels from H1, positive 20 decibels from H2, and negative 20 decibels per decade from H4. So, the overall slope becomes like this. Okay. And then from 4 to infinity, the slopes are positive 20 decibels for H1, positive 20 decibels per decade for H2, and negative 20 decibels per decade for H3 and H4. So, the overall slope becomes 0. So, that is my overall transfer function. So, this is Bode plot for H is that is the overall Bode magnitude plot. Okay. Now, if we are interested in developing the actual plot, then what we have to do is we have to actually plot the thing, and at some points the actual plot may cut the green line at some and at other points it may be somewhat parallel to it. So, this is the overall Bode plot. So, in this way we can construct the overall Bode plots for transfer functions which are not simple zeros or simple poles. Similarly, if we were interested in developing Bode plots for phase, we know that for a complex function which is a multiple of different simple functions, phase of the overall function will be phase of first part plus phase of second part plus phase of third part, and so on and so forth. So, what do I mean by that? For phase, so we have shown that we can break this H in this case as H1 times H2 times H3 times H4. So, then phase of Hs is equal to phase of H1 plus phase of H2 plus phase of H3 plus phase of H4. So, if we can develop individual Bode plots for phase plots for H1, H2, H3, H4, we can add them up and again develop the overall Bode plot. So, the method for developing magnitude plot and Bode phase plot remains essentially the same. So, this concludes our discussion on Bode plots and we will close for today, and starting tomorrow what we will do is we will start developing the one dimensional wave equation for sound propagation. So, thank you very much and I look forward to seeing you tomorrow. Bye.